So we are going to talk about joint inversion here. You heard Peter and Mike talk about processing of data, multi-component or otherwise. And so now when it's all done, we'll begin with some joint inversion on that. And we'll see how it compares with just the simple PP type of inversion. Now when we are talking about inversion, there are different kinds of methods we have for simple post-stack PP inversion. And we are not interested in these at present because the output that we get from any of these methods, that is just the acoustic impedance. When it comes to fluid or lithology information, that resides on the power offsets. And any methodology we have for pre-stack inversion, that is going to help us get that information more or over and above what we can get with simply acoustic impedance. Now, for just the simple vertical component data, we have simultaneous inversion. And the workflow that we adopt is something on the lines of this diagram that I'm showing you here. We pick up the gathers, conditioned AVO processed, amplitude-friendly AVO processed gathers, put them through this simultaneous inversion, and outputs are the P and the S impedance. And if we are fortunate to have long offsets or large angles, then we can also determine the density. Now we also can go through another workflow that we have been adopting, as an alternative, and that is Patti's approximation to the Zobrist equation we make use of, and first extract the P and S reflectivities, and then we go through this inversion of the P and the S reflectivities to get these two outputs. I will come back to this if I have the time, talk about a little bit about the fluid factor and another attribute that we've been working on. And again, as I said, if we are fortunate, we can determine density attribute as well. So, but when it comes to the multi-component data, here is the diagram explaining the geometry where we are talking about the common conversion points for the PS data. And here is, as you notice here, two things. One is the common conversion point is shifted from the CMP, and the other one is that the angle of reflection for the PS data is smaller than the equivalent angle that we have for the P data. And if we are able to just shift this at the location of the CMP, then we notice the angle of incidence for the same angle of reflection as the PP, that is larger. So talking about joint inversion, that means we have the PP data, we have the PS data. So we need to extract the wavelets from these two, and we also need the low frequency P and the S models to begin with. So when we have all these things, we put them into our joint inversion workflow, and the output is acoustic impedance, the shear impedance, and the density. Now, when we are talking about the post-stack joint inversion, obviously we are following a model-based type of workflow here. The reflectivities are modeled at for the post-stack data, 0 or something like 12 or 15 degrees, whatever the minimum angle is. They're convolved with appropriate wavelets, and then they're compared with the real PP and the PS data, and the error is minimized in an iterative way, and that's how we get acoustic and the shear impedance. When it comes to pre-stack joint inversion, we normally pick up three angle stacks, near, mid, and far, we call it. And here we have a choice as a user. I mean, we can have not three, but we can have 5 or 7 or more angle stacks. And then we extract the wavelet from these angle stacks, and then go about again following the same process, modeling the error between the model traces as well as the real data that is minimized in an iterative way. So for joint inversion, the workflow that we follow is like this. We of course load the data, PAP and PS data, correlation with the well logs, that is the first step. We'll have a quick look at this. So here I'm showing you the correlation of the PP data with the synthetics that we generate here. So we have the density and the P-wave log. The synthetic traces are in blue. The red traces are the real data. And we notice a good correlation here. Similarly, for the PS data, we do the same thing. And in this particular case, the correlation coefficient is reasonably good. That is not always the case, but here it seems to be quite good. Next step is the horizon event registration. And to do this, here I'm showing you a section from the PP data. And the horizons of interest, they are all picked up. We have the Cardium, Viking, and another one here. And the equivalent section from the PS data is shown here. And you notice there is that frequency content problem that Peter was alluding to. And Fred, it doesn't happen all the time. You get equivalent bandwidth for PP and PS. So then you bring this PS data to PP time by this matching of these horizons. And once this is done, we pick up the from the difference in the travel times of the PP and the PS horizons. We get this these isochrons for the given intervals. Here I'm showing you the PP isochron for Cardium to Viking interval. Similar on PS isochron for the same interval. And then you can quickly get the VP and VS that Peter referred to from these isochrons. Now this is a useful thing that we can pick up within different intervals. And at the well locations, you can see what is the range of values and look for any abnormal values that you may have on these displays, and that serves as a very good QC as well. Next step is this PP and PS joint inversion analysis. So you invert the traces at the location of the well so that you can compare them with the equivalent log traces. And so here is one such example where you have the V impedance, S impedance, the density, and the VPBS curves in blue. And the inverted traces are shown here in red. And this is a good QC to begin with. If these show a good correlation, now they match really well, then we are happy. And if not, then we go back and tweak some parameters and go back and forth again and again till we get a reasonably good match. Once that is done, we are ready to go for our inversion for the whole volume. Here on this display, I am also showing you the PP wavelet extracted and the PS wavelet as such. And this PP synthetic is just the P-impedance, inverted P-impedance, so that has been converted the wavelet to get this trace. It is compared with the real PP trace here. Error is given here, and similarly for the PS. So this is done. We run it on the full volume, and we are ready for our interpretation. Here is an example where we have the P-impedance section from the simultaneous inversion. And as you notice, I put on these arrows here, as you see in pink and blue, and then there is this dashed rectangle there highlighting that zone. Now we will compare this simultaneous inversion section with the equivalent section that we get from the post-stack joint inversion. I'll go back and forth, you have a look for yourself. The post-stack joint inversion is giving us better information in those highlighted areas, and it covers more or less the zone of interest here. So simultaneous and this one, post-stack joint inversion. Next, I show you the VPBS section that is derived from the simultaneous inversion, and this is the equivalent post-stack joint inversion VPBS section. Notice in the correlation that you have with the colored strip log there, it is much better with the one that we get from the joint inversion. Here I'm showing you the simultaneous inversion. Of course, I have to tell you that this is not a good comparison in the sense that we didn't have angles going all the way to 50 degrees or up to the critical angle for the simultaneous inversion. But there are people here, and I heard a talk at the Geo convention, someone said, well, we can just extract the density even if the angles are not up to 40 degrees, 45 degrees. Even up to 30 degrees, if you have angles, still you can determine density. Anyhow, I'm not sure if I agree with that. But the point is, here is the density that we extract with the simultaneous inversion, and this is what I extract with the joint inversion. And notice the difference between the two. So there is obviously value in looking at or extracting these attributes from the joint inversion. And here I'm only talking about the post-stack joint inversion. The pre-stack is still better, and that is about to come. Here I'm showing you the inversion analysis that is done with the simultaneous inversion. So we have the P-impedance that is available at the well, and this is the inverted trace P-impedance, and this is the relationship that you see between the two of them. And I show you a similar relationship or the graph for the joint inversion. We feel that it is a tighter set of clusters that we get with the joint inversion, and similarly for the S impedance at the well and at the inverted impedance, and this is simultaneous, this is joint inversion. Now how good they are, that will follow when you use these in your analysis further, when you extract the rock physics properties from these data sets. Here I'm showing you the lambda rho mu rho cross plot for at the location of the well, and you can see this is the distribution of the points in the different clusters. And if you pick up these points within this polygon there and backtrack them, you know that you see them that they are coming from the zone of interest, which is the Dubin interval in this case. Now this is the one that I get for a similar cross plot from simultaneous inversion. And then I repeat this process with joint inversion. You see the difference between the two. No separation between the points that you want to pick up here, and there is that bit of separation. One thing, you can pick up these points, and this is the same polygon that I picked up on the previous one that I showed here. You see the range here, 20 to 30 and 30 and 20 to 50 here, I think, and the same range is I pick up here. So it is closer to what I get with the well logs rather than with the lambda rho mu rho type of thing. And obviously this will have to be shifted into a different range to pick up the same set of points. Next I'll show you some examples from the Washout Creek, and there is going to be some overlap. Sorry Tim, I mean I didn't realize that Peter is going to show some slides and I'll show some slides and then you'll follow. But I'm not going to go into the finer details. I'll leave them for you to elaborate on. But we are talking about this Symposium formation, and it is the thickness of this is about varying from 5 to 25 meters in the zone of interest. Above this, we have the Leopard shale, and underlying is the Blackstone shale, and you'll see these on the next set of slides. You see here, this is the location of the survey, and this is what we are talking about, the Pembina field, and the southern tip of that is where we have the survey. Here is the Cardium sands, and this is the location of the Viking sand below. And the correlation coefficient for this comparison that I'm showing you for the PP data is about 0.757. Equivalent correlation coefficient for the PS comparison is about 0.80. That's really good. And here is the set of examples from the different inversion methods. And these examples are better. Right, Peter? They're more spectacular. More colorful. I'm showing you the black, these circles, they are the producer wells, production wells, and the white circles, they are the injection wells. And they are white injection wells because they are all injecting fluid. There is high sweeping water pressure there, and that is resulting in probably some lower impedance. So you see lower impedance where you have the injection wells, and these are high impedance Cardium sands that are showing the seen in the high impedance hot colors. So this is what we get with simultaneous inversion. The equivalent display from the joint inversion post-stack is somewhat like this. Now you can see that where the amplitude is bleeding here across all these linear patterns, that is more or less almost in line with the production well wherever they are. And then from here, this is the post-stack joint inversion. Then we go to pre-stack joint inversion, and you see the difference between the two. And if you are not able to make out much out of this, I'll put a grid on this so that you can see the different limbs where these different wells are sitting. So this was the P-impedance that I'm showing you. Then I also show you the density. This is from simultaneous inversion. This is from post-stack joint inversion. And this is what I get with pre-stack joint inversion. Notice pre-stack still gives us somewhat more detailed, more crisp definition of those patterns. Then a little bit about the future directions, the direction in which some of the work that we are doing here is going. And the first one is to show you about the spectral flattening of the PS data using the technique that we are using. It has to do with the generation of the average power spectrum and the average spectral magnitude. And based on that, we try and flatten the spectrum for the PS data. So this is the PP section. And here is, obviously, these are the horizons that we are interested in. And the equivalent section for the PS data, it shows somewhat lower frequency. And this is going to result in some loss of resolution when we carry out our inversion. So what we do is, this is the PS data in PS2A time. And after spectral flattening, this is what it looks like. So we have boosted up the frequency content here, and it has not gone, exceedingly out of the scale or something like that. But just to give you an idea, this is before we spectrally flatten it, and this is the one that is in blue, and the one that is in green, that is the one that we get after. And accordingly, you can see the difference in the wavelets also, slightly sharper wavelet after spectral flattening. Here is the P-impedance section using the PP-PS joint inversion, and the equivalent section after frequency enhancement or frequency enhanced version is seen here, and you can notice the changes that you have at the different levels. So we can make that difference happen to the data, and that will result in obviously somewhat more accurate interpretation. Here is the VPBS section that I'm showing you from the post-stack joint inversion, and this is what I get when I enhance the frequency content before doing this inversion. And finally, at the Viking level, the VPBS section, it looks like this before from the post-stack joint inversion, and this is what I get after the frequency enhancement. So there is obviously some nice definition of some of these blobs that you see there as compared with this one. You can make this happen. Then, I'm sorry, apologize for this. I didn't realize this was doing all this crap. I don't like it myself, so why share it to other people? The other thing, this is only in the last slide that I have, thanking you, let it go in a wavy sense, but I didn't realize, sorry about that. Using thin bed reflectivity inversion. And we can use this also to flatten the spectrum. So here is another example where I'm showing you the input PS data, and this is the spectrum. And then this is what we've done with the thin bed reflectivity inversion. Mind you, we have not gone beyond the high end of the spectrum, because I know some people are interpreters, they are a little nervous about that part, extending the bandwidth beyond the recorded bandwidth of the data. But that's fine. Either way, whatever you're comfortable with. So this is the after thin bed reflectivity inversion, and notice the changes that we bring about. Again, statistical wavelets extracted from the PP and the PS data, they are seen here. And once I do this, spectral flattening, notice the changes that we bring about. So once this is done, then you can look at the section, VPBS section from joint inversion before, and this is what we are doing, what we are getting after. Notice the continuity of these and the definition as such. Sorry. So obviously it is adding value to our interpretation. The next part is about the Poisson's impedance and Poisson's dampening factor, and we have been playing around with this. These were introduced some time back, and I'll just give you an idea. Of course, the details we can discuss later when we have the break. The idea is that we talk about the fluid factor, then when we extract the P and the S reflectivity using Patty's approximation from the Prestack data. And we talk about the fluid factor being the difference between the P reflectivity and the scale version of the S reflectivity. And it's supposed to be a fluid indicator. This work was first introduced by Quackenbush and others from Marathon, I guess, back in 2006, when he introduced this Poisson's impedance, and he said, well, this could be something very similar to this, except that it is now in the impedance domain. So you have acoustic impedance minus a scale version of the the shear impedance, and that should be a fluid indicator. So, later that work was followed by another guy. I thought I had put down the reference. Probably, yeah, this guy, Mazumdar, in 2007, again a leading edge reference, and he came up with this dampening factor, and he said, well, Poisson's ratio can be put like this, and if you just go through this this algebra and put it in this form, where this this term is put as d, you can write this as a Poisson's dampening factor. And the interpretation of this Poisson dampening factor is that it can give us an idea about the quality of the sands, where we can use Poisson's impedance to locate the phase sands better. And if you look at some of these curves, obviously this looks much better because individual units can be picked up better on this, but it doesn't give us much information about the quality of the phase sands, quality of the sands. So here is the Poisson's dampening factor, and it does indicate that the quality is increasing in this direction. So anyhow, the point is that now we are applying this not to just the gas sands or just the sands as such. We are applying this to shale plays, and this is again a curve or a cross plot between the Poisson's impedance and the Poisson's dampening factor. And as you see here, wherever you have the high Poisson's dampening factor, these are the clean sands, and I mean this zone as such represents the clean sands as compared with the rest of the stuff. And some of the shales, they will have this kind of location on the cross plot. So now, if we look at this for our intervals, like for example, here we have the Ireton interval, and here we have the Duvern interval. The Landau and the Muro type of attributes that we like to use, they don't show us the kind of separation that we expect. As you see here, all the way across is almost the same thing. Oh, they are overlapping. But if you go into this PI and the PDF cross plot space, you will find that yes, this one is giving you some crossover, this one is still overlapping. So in that sense, we are putting it to this application where we have the PI and the PDF, and on this cross plot, this is the PDF, high PDF, and should be resulting in a better lithology, and that is coming from the Duvern interval. Similarly, now on the real data, simultaneous inversion, PI and PDF, this is the kind of cluster we are getting. From joint inversion, you look at this, how the trend changes. From here, we are coming here, and then we'll pick up this one, and then backtrack it. This is coming exactly from the Duvern interval. Similarly, I mean, if we pick up another one, because this is the polygon where we found some of the points on the log cross plot, and this one again is coming from the same unit, except that it is a little more continuous, and you can always play around with this to see where exactly this should fit. But the idea is that this PI-PDF cross-plot space is a useful technique to look at. Similarly, we have talked about the E-row and E-row being a better attribute than mu-row. And we have not only published this, we have given presentation on this at different forums, but the idea is that E is the Young's modulus and is a stiffness constant. Poisson's ratio is a measure of the strength of the rock. And if we are to find out location of the pockets where we have high brittleness in shale plays, then we should be looking at low Poisson's ratio, high mu-row or high E-row. What we have talked about is that instead of getting mu-row, we should be looking for E-row, because E-row has a much better variation than just the mu-row. And if you want more details on this, you can consult our paper on this work in the May issue of the Leading Edge. But here, what we noticed was that in all planes, high E or E-row and low Poisson's ratio doesn't seem to be a universal indicator. Because in the Montany we've seen it doesn't work, because we don't get very high values of E or E-row. And in this particular case, in the Duvernay, again we found that it doesn't show us very high values of E or E-row. So here what we are getting is, we call it the moderate values of ELO. And here is the Poisson's ratio. And the equations to get these or derive these are given here. You notice if I take E on the other side, I only have IP and IS. And if I have IP and IS from joint inversion, I can easily determine this, or similarly from simultaneous inversion. And of course, Poisson's ratio, you're all familiar with. So if we pick up this polygon and highlight it or backtrack it, this is the Duvernay interval. Similarly, this is from the filtered log now, and I have filtered it to the seismic bandwidth, and you see that this is what we are getting. Just as we saw it here from the unfiltered log. Now, if I use simultaneous inversion, notice what the distribution is like. And then if I use the joint inversion, you see again where the points are coming back. So, I mean, these are small things, but you know, these days we talk about quantitative seismic interpretation. And I'd given a talk a couple of weeks ago in this very hall. And there you need to be careful about small things when you're doing this analysis. You cannot just take it for granted that, yeah, this is this one is here, so I must take this. This is good enough. It must calibrate with the law control. So you can try and get into these kinds of things. And notice here, this one is again coming from the same Duvernay interval. When you go to an arbitrary line of joint inversion, we get this kind of a trend. And again, this is very similar to the trend that we get from the logs. And so that gives us some confidence in the methodology that we are following. And again, we pick up that polygon, and it is actually coming from the Duvernay interval. And finally, I'll have a couple of slides. There are the girl sitting at the back waving my time is over. So in the 15 millisecond window from the ERO attribute, you see this kind of variation when you look at the simultaneous inversion. And when you look at the joint inversion, you see there is a difference, equivalent display. And similarly, if I show you the Poisson's ratio, again, you have this kind of a distribution from simultaneous inversion. But if I show you from the joint inversion, this is more like this. And this one is more like the ERO interval that I've shown you earlier, a couple of slides ago. And so these look more consistent than the simultaneous inversion. So to sort of summarize this 30-minute talk, which I don't approve of all the time, I like to talk more about this in a little more detail so that you follow what I'm saying. Here it was just a sort of a summary, not exactly a summary, but just to give you an idea of what we do here. Joint inversion performs better than simultaneous inversion. Some of the people in the industry, they seem to not follow this or do not agree with it, but our experience on not just these two projects that I've shown you here, or 2 or 3 projects, but on the many projects that we've done on inversion, they do tell us that, or they convince us that simultaneous inversion does not perform as well as the joint inversion, and the pre-stack joint inversion does give you better results from post-stack joint inversion. So pre-stack joint inversion gives you more detail, as I just mentioned, and for getting better results, we need to ensure that data conditioning, one thing, and P-PS frequency matching, they should also be considered because they lead to better results. So with this, I conclude my talk, and thank you for your attention.